In this video we're going to talk about methods for solving differential equations, like this kind of problem here. So we've got a variable x depending on a variable t, and we have the derivative dx by dt, which we'll also write as x dot, and we want x dot to be equal to f of tx for some, and here t is going to run from some range from a to b, say, and we've got the initial value that x is equal to x naught at t equals a. Okay, so if you actually want to solve these kinds of things in practice, there are things built into the standard Python libraries. The SciPy library has the solve IVP function, which will solve this kind of thing for you. But it's kind of important to have some understanding of what's going on under the hood and how it does that. So we're going to explore some methods we can just do directly. Okay, so first thing we're going to do, the most obvious kind of method is going to be is Euler's method. But let's just have an example to work with. Let's just have f of tx is x. So here we're trying to solve dx by dt equals x, and so that's a very standard example. So in that case, the solution is solution is just going to be x is e to the power t. Okay, but, so that's an example we're going to work with. And now so we're going to define Euler's method. So this is going to be a procedure that solves this equation for us. Okay, so as input, we need to know what the function is. So that's our first thing here. Is f is going to be this f. We're going to use this function here that we just defined, and then we've also got arguments a and b to tell us what's the range of t values, and x naught to tell us what's the initial x value. And then we're going to do this kind of step by step. We're going to divide the interval from a to b up into a whole bunch of time steps, and so we need an extra parameter which is going to tell us how many steps to do. And so we're going to divide the range, like I said, from a to b into well, let's do it. We'll have n plus 1 points, which means we've got n gaps. And for this, actually, we need to import import numpy as usual, and so there's so that's an array of times at which we're going to evaluate the solution, and then we're going to have we need to know the corresponding values of x. So we'll just make a kind of empty array to put the values of x in to start with. So we do np.0 is n plus 1. So we've got we've got kind of n steps, n plus 1 points, including if we include both ends. So we're going to have n plus 1 x values, and the initial value is going to be equal to x naught. Then we're going to take a bunch of steps. Okay, so we know what. So when we get here, we've worked out the first I values of x, and then we need to work out what's the next one. And we do kind of the obvious thing. We start with the previous value, and we're going to change it a bit. Okay. But actually, before we do that, let's just go back here. Let's put in h is b minus a over n. Okay, so that's the length of each step. Let's actually just put in a comment there. Yeah. Okay. So we're going to we've got to change the value of x, and you change it just by the derivative, right? So that's the standard deal with the derivative. The change in x is going to be the change in t, which is this h, multiplied by the derivative, which is going to be f of t comma x. But what's t here is just the ith of that entry in our list of times, and x is the that's we put in the old value of x. Okay, this f of tx is that's going to be the value of the derivative, and then we multiply by that by the change in t, That gives us the change in x. And then we need to return the answer, and it's convenient if we return the list of times as well as returning the list of x's. Okay, so that's our Euler method, and this is the key part of it. We just increase x by the time step times the derivative. Okay, so let's maybe just import plotting library as well, and then okay, so it's so here we're going to solve. We're going to solve x dot equals x for t running between 0 and 2, starting with x equals 1 at the initial time, and then we're going to plot the result. So yeah, we should have called that zeros instead of 0. And let's try again. Oh. Okay, so here we've got a graph, and it looks pretty much the same as the exponential graph, which is what we'd expect. But let's just check how accurate that is. Okay, and you can see you can see if you look closely that these graphs are diverging a little bit. Okay, so well, let's just see how much it's diverging. Okay, so let's plot the difference between. Okay, so it's going down to it's got a difference of minus 0.14. That's not great. You should very typically sort of try and do calculations, and we expect to get like 10 digits of accuracy or something. Here we've not even got the first digit correct. So this is not such a wonderful method, and also we did have to take 100 steps for that, and if we try and do it with bigger steps, still we've got steps the size of 0.2. We're not talking like enormous steps here, and then if we actually plot both things together, okay, so you can see that this method is diverging, and so the first thing is the blue curve is our solution, and the orange curve is the kind of true exponential, and you can see that the blue is consistently below the orange. And so why is that? I mean, and the reason is, so we're supposed to update here. We've got the old value of x plus h times this thing which is supposed to be the derivative. But this thing here, this is actually the derivative at the beginning of the time step. And in an example like this, the derivative actually increases throughout the whole time step. And so if we just use the derivative at the beginning, it's kind of not big enough. So let's see if we can try and improve that a little bit. Okay, so so let's just copy this. I'm going to define a new method that's called the midpoint method. So we're going to do so instead of doing this thing here, we're going to try and work out what should be the derivative at the middle of the time step instead of the beginning of the time step, because that's kind of more likely to be accurate. So what's the time at the beginning of the time step? Let's call that tt. Okay. And then now we need to know what's actually going to be the value of x at the beginning of the time step, at the middle of the time step. Well, we don't actually know that. That's kind of the kind of thing we're already trying to work out. But we can just use the midpoint method to try and work out what's going to be x at the middle of the time step. So we do the same sort of thing here. We just take our old value of x, Okay, so that's the value of x at the middle of the time step, or it's that's a guess at that, which is kind of based on the Euler method. And the Euler method, as we said, is not so great, but for current purposes, it's kind of okay. So now here, what we're going to do is, instead of the previous thing where we calculated the derivative at the beginning of the time step, we're going to calculate the derivative at what we now think is the middle of the time step, ttxx. Okay, so this, and so this is hopefully a bit better. So let's go back here, and instead we'll do the midpoint. Okay, now you can, if you look very closely, you can see that there is a tiny gap between these two graphs here, but that was only with 10 steps. And if we go back to 100 steps, right, then there's no difference at all. So at least there's no visual difference between these two graphs. We could okay, so we've got if we actually just plot out the error rather than plotting the two graphs together, you can see you've got an error around 10 to the minus 3. So it's still not brilliant, but certainly better than with the Euler method. And then there's a bunch more much fancier methods that one can use that go kind of in the same sort of direction. I mean, here we just went to the midpoint to make a better estimate for the derivative, and you could think about sort of taking further small intermediate steps and messing around with those to try and get a better idea. There's, for example, there's the Runge-Kutta methods, which are of that type, which we'll discuss in a separate video. That's at least enough of an initial indication of the kind of considerations that go into designing these algorithms for solving ordinary differential equations.